So our last topic was all about algebra, pronumerals, things like that. Very important part of what we do in maths. Well, now let's look at the actual numbers themselves, which are extremely important in maths. So the real numbers, because essentially that's what we deal with at the moment, real numbers. We have our set of real numbers. What makes a real number a real number? Anything that you can place on the number line. Or more correctly, the real number line. So the number line is actually called the real number line. The symbol that we use for the set of real numbers is R, but it's actually what we call the hollow R. Now inside the real numbers, we have rational numbers. Now what are the rational numbers? Symbolized by Q, by the way, for rational. You think, well, hang on, Q, rational? Well, we've already used R, so why do they choose Q? Quotient. Because rational numbers, of course, are anything that we know exactly, but more importantly, anything we can write as a fraction. Then there's the other set, irrational numbers. Well, the prefix IR just means not. So anything that's not rational, we say is irrational. Okay? Now, we don't actually have an abbreviation for irrational numbers. So the notation we tend to use is that. You won't see it that often, to be honest, but it's R\Q. So the backslash just means not including. So the real numbers not including the rational numbers, you're left with the irrational numbers. Okay, inside the rational numbers, we have, well, I've called them fractions, and by fractions, I'm meaning the ones that can't be simplified down to be whole numbers. I mean, technically, whole numbers are still fractions, because you can write them as over 1. But I'm thinking about the ones that can't be simplified down to a whole number when I say we've got this set of fractions inside. Then we have the integers, the ones that can come down to be a whole number. And the symbol for integers, of course, is Z. Where does it come from? It actually comes from German. So the German word for integer is Zahlen. So that's where the Z comes from. Inside integers, we have our natural numbers, symbolized N for natural. So we have the natural numbers. Natural numbers are, of course, positive integers. Which then brings us to this other very special number, 0. And some people say it's not actually a number because it doesn't exist, so how can it be a number? But 0 sort of sits by itself. Then overarching all of these, so it intersects, we have the negative numbers. So you can have negative fractions, you can have negative integers. Notice it doesn't overlap the naturals or 0, you don't have negative 0. And you can have negative irrational numbers. So that's basically our family of numbers that we use. Okay, how do we work with them? Factors are so important. That's why in algebra, factorization, we play so much with. So being able to break a number down, every natural number, so every positive integer, can be broken down to be a product of its prime factors. So for example, 324, well I know it's 4 18s, but I can keep going, they're not prime. But there we go, 2 squared times 3/4. 2 and 3, of course, being prime numbers. Also explains why we don't consider 1 to be a prime number. The actual definition of a prime number is a number that has exactly 2 factors, 1 and itself. So 1 does not fit in that description. If 1 was a prime number, I couldn't do a prime factorization because I'd be going times 1, times 1, times 1, times 1, times 1, and then you just keep going. Highest common factor. How do you work out a highest common factor? Well, you write the 2 numbers in their terms of their prime factors. Then you pull out the common factors. So it's just like factorization in algebra. In fact, that's what we're doing in algebra. We're working out what the highest common factor is. So here's 2 numbers. 1,176 ends up being, eventually, there it is, 3 times 2 cubed times 7 squared. 252 is 2 squared times 3 squared times 7. So to work out the highest common factor, as I say, it's just like factorizing in algebra. We pull out the factors. And when we're factorizing, you always pull out the lowest power. So yes, 2's in both, but 2 squared would be the lower one. So 2 squared goes in there. 3 to the power of 1 goes in there. 7 to the power of 1 goes in there. So 84 is the highest number that would go into both of those. So remove the lowest power. Lowest common multiple, same deal, we start by thinking about the prime factors, but this time we write down all the factors without repeating. And this is what we do in algebra when we're finding our denominator, the lowest common denominator. It's the same thing. Two numbers for this example, 48 and 15. So 48 is 2 to the power of 4 times 3. 15 is 3 times 5, so lowest common factor. If it's not there, put it down. So 2 to the power of 4, not there, put it down. 3, not there, put it down. 3, oh, it's there, I'm fine. 5, put it down. That would be our lowest common multiple. So that's the smallest number that both 48 and 15 go into. Divisibility test can be handy when you're trying to work out factors. Oh, geez, does 3 go into this? Does 4 go into this? That sort of idea. 2's a real easy one, of course. Anyone know the divisibility test for 2? No, it's an even number. Okay. Divisibility test for 3. So all the digits of the number will add up to be a multiple of 3. 4, key is the last 2 digits of the number. Okay? So if the last 2 digits of the number is divisible by 4, then all of the number is divisible by 4. Why does that work? Well, because 100 is divisible by 4, we know that. So we don't need to worry about the numbers after the tens column, if you like. We only need to look at the last 2 digits. 5, yeah, got to end in a 5 or a 0. 6, well, we simply just say, well, it's an even number that is divisible by 3. So all the digits add up to be 3, but it's even. So it's got to be 6, divided by 6. Now here's the one. This is the first one where people go, ooh, 7. This is tricky. There it is. Double the last digit and subtract it from the other digits, and if that answer is divisible by 7, then the whole number is divisible by 7. Whoa, show you what I mean. Give me a number, please don't say 14 or something like that. Give me a number which is divisible by 7. Grab a calculator, pick a number, go multiply by 7, tell me what the number is. 707. So what's our rule saying? Double the last digit. So the last digit is 7. If I double that, I get 14. Subtract it from the other digits. Well, it looks like now I've got the number 70. So subtract that, 10 minus 4 is 6, 7 minus 2 is 5. Does 7 go into 56? Yeah, 7 8s are 56. Therefore, 707 is divisible by 7. So that's how that one works, and it's the one everyone forgets. 8 is a bit easier. This time it's the last 3 digits, we say. Well, okay, last 3 digits will be divisible by 8. 9, sum of the digits is divisible by 9. See, 9 is 3 squared. So it's got the same sort of feel as the divisibility test for 3. 10, of course, is quite straightforward. Ooh, ends in a 0. 11 is another interesting one. The sum of the even position digits will equal the sum of the odd position digits, or they will differ by a multiple of 11. Okay, give me a number that's divisible by 11. What is it? 132. The sum of the even position digits. Well, there's only one even position digit. There it is. It sums to be 3. The sum of the odd position digits, 1 and 2, totals to be 3. They total the same thing. That's divisible by 11. Okay? So that's the idea on the 11 one. Doesn't look like I've got room to put 12, so I might have stopped there. But there are tests for 12 and all the others and so on. Okay, fractions and decimals then. Let's have a look at these things in particular. More importantly, let's look at converting recurring decimals into fractions, because the other ones are pretty straightforward. Right, converting a fraction into a decimal is easy because a fraction just means division, so you go top divided by bottom, you get the answer. Converting a terminating decimal into a fraction is easy because of our number system being base 10. And we know we have the tenths column, the hundredths column, and that. Easy. Recurring ones are the ones that are interesting. Let's start with one which hopefully we just know what is. 0.6 repeater. Let's pretend we don't. Here's a technique that people often use. We say, well, we know this to be 0.66666 and so on. I'll let x equal that. So x is 0.6666 and so on. I'm going to multiply it by 10. If I multiply by 10, I get 6.66666. So whilst those 6's go on forever, I can subtract, because I know in every position, the tenths, the hundredths, they have the same number. So if I subtract, they will disappear. And I'll be left with 9x is 6. So x is 6 on 9. It simplifies down to be 2/3. So that's 0.6 repeater. That's the idea. Now if I've got two numbers repeating, so 0.81 repeater, which is 0.8181818181, I can use the same idea. So I'll let x equal that. Okay, I want to get the 8's and 1's in the same position. So multiplying by 10 is not going to be any good now, because I'll get 8.181818. I won't have the same thing. So if I multiply by 100 in this case, that'll get them the same. They've both got 0.81818181. I can now do that trick. Let's subtract. 99x is 81. 81 on 99, which simplifies down to be 911. Okay. What happens if not all the numbers are repeating? So we've got 0.3, but then just the 2 and 7. So it's 0.3, 27, 27, 27, 27. It's okay. Still want to just make the repeating ones the same in the columns. That's what we want to do. So let x equal 0.3, 27, 27, 27, 27. If I multiply by, I think 100 will work for this one. Yeah. If I multiply by 100, then the repeating part, 27, 27, 27 lines up. I can do a subtraction, and I get 99x is 32.4. So x is 32.4 and 99. We don't normally see decimals inside fractions. That's unusual. Okay? Like, we either use a decimal or we use a fraction. We don't use both at the same time. So I multiply top and bottom by 10, and I get 324 and 990. Simplifies down, that one's 18 on 55. That's the way mere mortals do it. There is an easier way. Anyway, spot a pattern, use it to your advantage. Here's how I do it. I look at 0.6 repeater, look at that and go, well, the top of the fraction must be 6, because that's what's recurring. The bottom of the fraction must be 9, because there's one number recurring. So I'll put down 9 on the bottom. And there's my answer. 0.81 repeater, same idea. Well, 81 goes on top because that's what's recurring. 81, 81, 81. Now, here's the clever bit. There are two numbers repeating, so I write down two 9's, and by two 9's, I don't mean 18, I mean physically write two 9's, 99. So however many numbers are repeating, that's how many 9's I'm putting down. 81 on 99, 9/11. Which means if I had something like this, 0.7134 recurring. So 7134, 7134, 7134, 7134. Same idea, there's my answer. Straight away, got it. What's recurring? 7134. How many? Well, there's four numbers recurring. So I'll put down four 9's. 9999. Simplifies down, does it? Yeah, there you go. 2,378 on 3,333. So much quicker. By recognising the pattern, bang, you get the answer. Well, what about the one where they didn't all repeat? Here's how you get this one. On the top of the fraction was 324, you'll remember. Why is it 324? Because 324 is 327 minus 3. You subtract the number that's not recurring. So 327 minus 3. On the bottom of the fraction is 990. There are two numbers recurring, so I put down two 9's. But there's a third number. I put down a 0 for that, because if I didn't put the 0 there, well, it's not going to be true over 99. I need another number there to make it the fraction. We put 0 there, 80 on 55. So if I was to get something like this, 0.1096 repeater, so 1096969696, I can just look at that and say, oh, well, that's 1086, because the number is 1096 minus the 10, that's not recurring, over, four numbers there, two of them are repeating, 9900. Two numbers repeating, two 9's, two numbers are not repeating, I'll put down two 0's, there's my answer, 181 on 1650. Okay. Spot the pattern, make your life easy. Okay, that will do us. So exercise 2A, I've also photocopied from the old Cambridge book some questions. For some reason they didn't put those in this exercise 2A when they made a new edition, don't know why. They're nice questions, so I thought I'd add them in.